He worked for Google, IBM, and he has a very strong background in file systems. So welcome, Srivas, and enjoy his talk about the architecture, about MapR, and probably a lot of insight in the file system. So thank you.
Thank you. So this is the best HUG I've ever been in. Inside a disco with lots of beer, and they gave the beer before the talk. So I was in Paris yesterday. Wait until the HUG got over. Only then people got beers, and it wasn't single beer. So anyway, to get started. So this talk is more about, I keep getting asked by everybody, what did MapR do? What is it? How is it different from all the Apache Hadoops? Because everybody says Apache Hadoop. It's at the core, it's the same thing, whether it's Cloudera or Hortonworks or Intel or everybody. And so I thought I'll just make a bunch of slides around that. So quickly, my background. I used to work at Google on search. As part of search, we used MapReduce quite a bit to build a search index. And before that, I was working on Bigtable at Google. And before I joined Google, I was chief architect at a company called Spinnaker Networks, and that got acquired by NetApp. So today, NetApp's flagship product is Spinnaker Network, is the Spinnaker product. Anyhow, some quick history of MapR. Google published the MapReduce paper, Yahoo copied it, then Facebook started using it, Twitter, LinkedIn, everybody started using it. And so at Google, where I was working at that time, we got a bit worried. We said, oh, did we make a mistake publishing this? Is Hadoop a threat to Google? So we took a close look at Hadoop when I was in Google, and we said, oh, it's not a threat, no problems. But this is very interesting. I was thinking in my mind, hey, but everybody's using it. We know it's not a threat, but it's very useful. It's good quality is so-so. Maybe there's some money to be made here. And then we had the stock market crash, where everything, the bottom fell out of the market, and some 20 different insurance companies declared bankruptcy. And I said, oh, this is a great time to start a company, because everybody is busy trying to recover. So let us go and raise some money and start a company, and nobody will do any new development at the time. So the timing came out very nice, lucky. So we founded MapR. We shipped the first MapR distribution in 2011, in the middle. And this was very interesting, that happened almost immediately. Google kind of invited MapR to participate in the Google Cloud. So it's kind of coming full circle. So today, the Hadoop distribution in the Google Cloud is MapR. Amazon Web Services also invited MapR to provide Hadoop in the cloud. So it's kind of big validation to see the two biggest companies in the world that know about MapReduce and how to do very, very large scale computing invite MapR to be a partner. And then we broke all the world records in Hadoop. And then then this year we released like the fastest NoSQL. And we also are very proud to announce that we became one of the largest non-Web 2.0 commercial installation of Hadoop. Okay. So one of our very, very big customers is now running a very massive cluster. So this is a nice marketing slide. More marketing, but let me tell you what this is. Basically, MapR gives you all of that's in Apache Hadoop. So everything you get from Apache, you have in MapR. But we also have done a lot of work in the data layer and in the management layer. And this talk is really about what we did in the data layer. And not specifically file system, but what does it take to make a cluster reliable? And why did these two guys pick MapR to be on the cloud? Okay. In the cloud, there's a very interesting problem. If VM crashes, well, the cloud provider will move the VM to another physical machine and everything recovers and everything runs. But what about the data that you wrote on that node? That data disappears. And MapR was designed from ground up to make that reliable, right? So what makes it so reliable? So very simple, you all know how to do this already. You make a cluster reliable, you make the storage first reliable, then make the services reliable, and the way you do that is save the state and the data in the storage above, and use Zookeeper or something to detect the failure, and move the service to a new node when there's a failure. Well, so what's so difficult? Well, it's doing it fast. So the problem is you have to do it very fast and without any maintenance windows. Right? So, and then on commodity hardware, what's the challenge? There is no NVRAM. NVRAM means non-volatile RAM. You cannot assume special connectivity. You cannot even assume more than one drive per node. So you cannot do anything like a RAID because you only have one drive. And you can use replication, but you cannot assume that the two copies are the same size. What if one copy is 10 times the size of the other? Right? So then how do you do replication? So, but there's no choice really. So how do you do replication? Well, it's easy, right? You, on the left side, you have the client send some data to the primary copies to the secondary, everything is happy. If you're trying to do Cassandra, you do the thing on the right side, which is the client gives to both the primary and the secondary. But failures happen, and this is the fundamental problem. Detecting the failure is easy, but until the replica comes back and is ready again, you're exposed to data loss. And this is the number one problem in any cluster that's there. In the picture on the right, in the Cassandra model, since the client did the replication, you have this eventual consistency problem because the client that did the replication went away. So unless you run a special client called anti-entropy, it stays kind of out of sync until you run that. And so anti-entropy causes a cluster outage because you have to check everything and make sure everything's okay. So not very good. So unless it's Apache HDFS. So it solves the problem a third way. What do you think it does? Anybody? What do you think? How does Apache HDFS solve this problem? No? So very simple. It makes everything read-only, right? So there's nothing to resync. And so that's why you see the semantics from HDFS. It says single writer, no reads allowed while writing, which means nobody can see the data you're writing right now. And the file closes the transaction that makes the data ready. So it's like saying, if nobody saw the data, maybe the data did not exist, right? By the way, this, for what HDFS was designed, it's not so bad. I mean, if you're doing web scraping and building the World Wide Web Index, or you're doing, recommendations in Amazon for a product review or something, that's great because who reads a product review, right? And if you missed a web page today, you'll find it tomorrow. If you do a search and it probably never saw the data, it's okay. But companies like banks, telecommunications, airlines, and all cannot run like this, right? And the same reason you cannot do real time with HDFS. And you can see each base kind of, as Lars pointed out earlier, it kind of suffers from this problem because it has to deal with this problem where to make the data visible, you have to, the only way you can do it is to write and quickly close the file. But then if you do that fast, you have too many small files and HDFS rolls over. And so it can never do NFS because of the same problem, because there's no close in NFS. So so what HDFS does is try to take a guess when to close the file. So, oh, here's some data, let me give some timer. Oh, I have 3 seconds idle time, let me close the file. Well, what if a write arrives right after that? Because a client can cache the data anytime, or application can suddenly wake up and it's logging data slowly. You lose the data again, right? All right, so 21st, so let's come back to the real problem, because most people need read-write. You can't do this. So the question is, how long does it take to resync? If you have a 12 drives per server, 2 terabytes per drive, 24 terabytes at a gigabyte a second, you will go for 7 hours. 35 hours if it's half the speed. But if you want to do it online, then you're down to, it will throttle it. And then you're down to 15 days to resync that. Right? Why is this pretty bad? If I have, let's say, 10 drives per node, and I have a 100 node cluster, that's 1,000 drives. The mean time to failure between, for a drive, how long it lasts, is about 3 years. So if I have 1,000 drives, I have a drive failure every day. Right? So I cannot wait for 15 days to resync. So basically, how long before, whether you're doing double disk failure or triple disk failure, what is your mean time to data loss? And that's extremely important when you're designing a system. Right? So what do all the commercial guys do today? NetApp, EMC, Isilon. So what they do is they create this RAID 6 array with extra drives, with the NVRAM and everything. They put a dual port. Primary and replica has the same, they copy the NVRAM over. And then when a primary dies, the secondary takes over, nothing to resync, we're done. Right? I used to sell this as the thing that NetApp purchased. But you wanted to do commodity hardware and large-scale clustering, you can kiss that goodbye. And back to 5-year spare parts plan, where you try to do 5-year contract, to make sure you don't get screwed later. And what about performance? You're back to this architecture, where you have the traditional RDBMS sitting on a SAN, some JBoss or some homegrown application, and stored procedures and all that stuff. No performance. Versus, you really want to do that in Hadoop. And so, people want to do geographically dispersed, which you cannot do at all with the solution on the left. All right. So what does MapR do? So what MapR does is, so these yellow boxes are nodes in the cluster. And what it does is it chops up the data of any node into like 1,000 pieces or 2,000 pieces or something. So if I have 24 terabytes, each of these pieces is 24 gigabytes, and you kind of throw them around on the cluster. Right? You spread it around the cluster, so you take this node, break it into pieces, and spread the copies around. Right? 2 copies everywhere. So why does this improve anything? So I'll work through an example, and let's work through a 100 node example, the same example. So 100 node cluster, and so if I do this on every node, then every node will have 1/100th of every other node's data, right? And when a node crashes, the entire cluster will resync the data. So you die, and the resync happens. So what happens is you have 99 nodes now resyncing in parallel. You have 99 number of the resources. So 99 number of drives times the number of drives, 99 number of Ethernet ports, 99 times the number of CPUs, 99 times the number of DRAM, everything's 99. Power supplies, everything. And each one is resyncing 1/100th of the data of that one big node. So what do you expect? So the net speed up is about 100 times. So you'll come down from 350 hours to 3.5 hours. And so your mean time to data loss is about 100 times better. Very nice. Right? Now I can live through those disk failures. In fact, if I increase the cluster size, this number actually improves. So why is this so difficult? Why don't other people do it? Right? The real problem is that MapR is doing synchronous replication on commodity hardware. So what we're doing is, if I look at this container, the writes are synchronous. The clients write to a master writes to a replica 1 writes to replica 2, and all the replicas have to reply before the master says, oh, the data is good. Now remember, it's not eventual consistency, this is strong consistency. So which means a read going anywhere can see the data no matter which copy it goes to. Okay? And there's some nice things over here on the side. And so what it does, what each server does is it keeps a bunch of these containers ready to go and starts spreading the writes as the system runs. Right? So as the data size increases, it spreads out more like, you drop a pebble in a pond, right? The larger the pebble, the bigger ripples, it spreads further and so on. So, and the space is balanced by moving the idle containers. So if one of the nodes gets into trouble, we can increase the replication factor for one of these things to, let's say, 4. So for example, where's my mouse? There. So I can add a replica over here between this node and a new node here in order to move this one away. And what that does is I can make space, in this node by involving 2 other nodes here without impacting the node that's in trouble. Okay. Anyway, so now let's explain why this is so hard. Let's say these are 3, so time, think of time going from top to bottom. So there are 3 replicas going in happily in sync from top to bottom, and one of them crashes. Well, it's not a problem, you can resync it from the other guys. It's not that much data, it's 24 gig. But what happens if all 3 crash? How do you figure out who's the new master now? Because since we are trying to do update at a very, very high speed, they will all diverge. You have lots of operations outstanding, and each copy is committed a different set of operations. So they all diverge. So what do? Right? So what MapR does is every copy can individually detect where all the other copies have diverged, even at 2 gigabytes per second per container. At very, very high speed. And so what we do is we can arbitrarily pick any copy as the new master, any one of them, and then roll back the others and roll forward down to the new resync point. Right? Put them in sync. And we can do this online. And this is an extremely hard problem that we spent 2 years trying to perfect and get going and all that. Right? Let's scroll over this. Okay. So, having built a cluster now that's extremely reliable and extremely fast, where do we exploit this in Hadoop? Right? So, what do? So, the first thing we did, we created this no name node architecture. We took this problem in Hadoop, which is the name node, which has, which really was a single point of failure, runs everything in memory, cannot really scale beyond a certain size and all that. And we took the data in the name node and threw it on the cluster and said, just treat it like any other data. It's fully transactional. And we found that we could scale really well. So here's the performance comparison. We ran the name node benchmark, 10 node cluster. We're creating 100 byte files. So right, remember the same problem I talked about real time, you create a file, close it, and so on. So we did that. So the blue line on the top is MapR. So x-axis is number of files, y-axis is the creation rate. So the blue line, so it goes up to 1 billion, and at about 15,000 per second triplicated. Versus, and so that can keep going, there's no problem. The red line on the bottom is Apache. I don't know, so I exploded it up over there in the red circle. So it's about 4,000 times slower, no, 40 times slower, sorry. And kind of stops at 1.5 million files on a 10-node cluster. And that cliff falling down is Java going into infinite garbage collection in the data node. So you cannot create really more than 1.5 million files on a 10-node cluster. So of course, as you increase the cluster size, that number will move to the left, but it's not going to go very far, right? Because you really have to have a million node cluster to get to where we are. With MapR, of course, if you double the number of nodes, that blue line is going to double in height. So you just double the rate flat out. So where else did we use this? We built NFS so that you can directly access MapR. Any server can log directly, whether it's a web server or a database server or application server. And all databases do fast export and fast import. Bulk export and import of data is native. And so you don't need any connectors. You can have the entire MapR cluster behave like one giant NFS server. Where else did we exploit it? We created this thing called volumes, so that we give you control over how to do snapshots and mirroring, cross data center operations. You can control data placement in a cluster and things like that. Where else did we use this? We created this thing called M7 tables, the NoSQL, the fastest NoSQL on the planet, like I said. And it's actually 100% compatible with HBase. So you kind of just change the name of the table and it picks up M7 or HBase automatically. And we kind of stepped around all of the problems that Lars was describing. Because we don't do any compactions. Because we can update in place. Right? We don't have this problem of how do I make the data visible. I'm going to write all these files and then one on top of the other and there's a wall and all that stuff is not necessary. It's instant on, 0 recovery time. And it's about 10 times better performance in some situations. It's a whole order of magnitude better. Here's some example of the performance. This is running HBase 94.9 on a 10-node cluster. On the x-axis is the time, y-axis is the throughput operations per second, and the red line is Apache HBase with the table pre-split. We loaded about 2 terabytes of data. We ran the Yahoo Cloud Serving benchmark with a 50-50 mix. And with MapR, we started a table, we just created the table and do auto splitting out here. So because of auto splitting, as as the data size increases, it splits and more servers gets involved. So like in the beginning over here, there's only one server running. Where's mine? Lost my mouse, okay. And as the table splits, more servers gets involved. So you see the curve rising up until you hit the limit of the cluster, which is 10 nodes. And then as the data size increases, it kind of levels off. It falls down a little bit and levels off. And that's about 8 times faster. On the right side, y-axis is the latency. And the yellow dotted lines are Apache latency. And the dotted blue line, which I'll show on the next graph, is the MapR latency. So 95 percentile, 99 percentile is flat. Right, so we were able to do this with pretty good performance. The reason is we are directly accessing the data without any fancy. Actually, the code is simpler than HBase, but we get the performance. And these latency spikes, some of them go to the 3rd floor because this is kind of magnified. Right? If I go back to the previous one, see some of those big peaks there? When the latency is that high, I don't call it high latency. It's a hanging. So it's basically garbage collection running in the HBase region server. So across the board, we did some numbers on, on various things on SSD and this thing, and we're about 10x faster, 11x faster. Where else do we exploit? We really make Hadoop truly HA. Like, so for example, yarn. Right? We use the same technique we talked about. We write the state and the application master or the job tracker in MapR, as well as the data. And on a failure, we can restart that job anywhere in the cluster exactly from where it was. So if a job is completed at 83%, it's going to start at 83%, even if you reboot the whole cluster. Because it's automatic. We don't have to do anything further than just making these simple things. Right? It's only from MapR, right? And as a matter of fact, we found something very interesting, which is when we do this, when you crash a program and restart it, if you do it involuntarily, it's called HA. If you do it voluntarily, it's called preemption. Right? So we could do preemption, which means we can take any job, stop it, restart it later. So we exploit that for this thing called express lane, where if you have a cluster with, let's say, a big batch or a lot of big batch jobs running, and you insert a small interactive job, and you want that interactive job to jump ahead and run so that it finishes. Right? This is very normal. We do that. What we do is we preempt the one that's running currently, take out a few tasks, and let the new job start there. And if it's a small job, it finishes, and we're done, and we continue the old job. But how do we know it's a small job? Well, we don't really care. We just let it start, and if it doesn't complete, it's not a small job, we preempt it. Right? And we put it back to the end of the queue, so it's a big job. Exactly like any Linux scheduler does. The interactive response is very nice. The batch response is also good, but doesn't get in the way of the interactive response. And by the way, we didn't have to do any fancy statistics about the job size and the amount of data and blah, blah, blah. The code is actually simple. Right? And so, if you look at some of the records we were able to break, we broke both the minutes, the terasort record. Terasort is how fast can you sort a terabyte. Actually, now the new number is, I think, 45 seconds. We can use 45 seconds. So think about the problem here. You're sorting a whole terabyte in 1,000 nodes in 45 seconds. So you have 15 seconds for a map, 15 seconds for shuffle, 15 seconds for reduce. In that 15 seconds, so if you have 1,000 nodes, 1 terabyte on 1,000 nodes is about 1 gigabyte per node. You have to read a gigabyte in the 15 seconds, sort it, and write a gigabyte out. So that's the map. The reduce is now transfer the gigabyte over the wire and merge it for the reduce side, and then write a gigabyte up again. So there's basically no time left to schedule or do anything here for fun. Right? It's basically running, there's no time left at all. We just have to run as soon as possible on everything. So there's a hell of a lot of optimization we did to get this thing to run so fast. Then we ran the second minute sort record, which is minute sort is actually now the opposite of the terasort, which is given 1 minute, how much data can you sort? We sorted, the previous record was 1.4 terabytes held by Microsoft on the Dryad framework, using Link and Dryad inside, using something called FDS in the Microsoft Research Lab. So we broke that. And then one of our customers decided to break our record. So they were purchasing about like 1,000 node cluster, the 300 nodes had arrived, and they said, hey, let our IT guys have some fun, let's run it. And so they broke the record, and I think right now they're at about 1.8 terabytes in 1 minute. So you can do the same. Like when you use MapR, all your code is automatically HA. Save the service state, save the data, use Zookeeper to detect the failure, and then bring it up anywhere. The data will follow, the state will follow. Don't worry about that. And by the way, that's what we did to make everything HA, right? So everything in Hadoop is really HA from MapR. And it doesn't matter what it is. Whether it's Impala or Hive or Uzi or Storm or MySQL or Postgres or HCatalog or whatever. Lucene, Solar, Kafka, anything. And since we're fully read-write, we don't really care what it is. It does it. And by the way, all this code is in our GitHub. You can get it at any time. I think there's all kinds of different fancy code up there to show you how to do this. So basically, what we set out to achieve when we started MapR, I think we have achieved now, where we want to get you to be able to build a cluster, node at a time, brick by brick, on dirt cheap commodity hardware, right? At 1/10 or 100th the cost of a NetApp or a Isilon or a EMC or anything. But get the same kind of reliability without having to pay for this fancy force field for yesterday's hardware. You're paying a lot of money. And export this through any kind of software. So here's some good links. If you want to talk to me or contact me, that's my email. Happy to answer any questions there. And there's some good websites which are actually not BS. I mean, they're not marketing. Okay? They're actually real good websites. The one at the bottom is a little bit more marketing. So you can skip some articles there. So any questions? Was this useful? No questions?
I will put one question. Now because it's the new version of Hadoop, also including YARN. How do you see the conference now coming up, and what do you think about the Storm implementation? I don't know if there is already...
Okay, very good questions, right? So, the question is, new Hadoop got released yesterday or day before yesterday. It has YARN. What's your comments about that, and how about Storm? Yeah, right. So, like I said earlier, everything in Apache we ship. So we're shipping YARN eventually, because I think this still has to get a little bit more stable. Because the way Apache releases code is kind of different from the way, let's say, a MapR or a Cloudera will release code, which is when we release the code, it's actually very stable and working well. Right? Versus Apache will say it's released, and then they say, okay, now everybody use it and tell me what the bugs are, we'll fix it. Right? So it's kind of a different QA approach. But we include YARN, but MapR's approach is to really test it out, get the performance up, get it fully HA. Because for our customers, they want to do like one upgrade a year. They don't want to do more than, if I have 1,000 node cluster, I'm not going to upgrade more than once a year, and that's already too much. Right. So we are very, very careful when we do releases. Our quality is extremely high. So you may be a bit early on some features, a bit late on some features, but that's okay. So Storm is a message passing. How many of you guys know what Storm is, right? It's a message passing interface. So one Storm process does some publish, subscribe, and gives it to the second one, and so on, right? So YARN can schedule Storm in the cluster, so it doesn't conflict with resources with MapRs or something else, and that's good. But to make Storm reliable, you have to put something like Kafka underneath. And what Kafka is basically a publish-subscribe system with reliable queues. Kind of, right? So actually with MapR, you don't need Kafka at all. In fact, Ted Dunning, pretty much in 2 days, wrote something he calls Europe, which is the younger brother of Kafka. And it does the queuing in MapR itself directly without requiring all the, because 90% of the code in Kafka is about how to make it reliable. And it's actually more reliable than Kafka. So that code is also there in, on I think, wherever in Ted Dunning's GitHub or somewhere. So you can get that. But it's available from us. Any questions?
Okay. So thanks a lot for the nice talk. And again,